Hi class, and welcome to our next video lesson on nuclear energy. We're going to talk a lot in this video lesson about nuclear reactions and how nuclear energy is actually used and can be used for a lot of in our everyday lives. But before we begin and get into some new content about nuclear energy, we're going to go back and talk about something that we discussed at the very beginning of the year because it's actually the root of nuclear energy, and that is the atom. We started our year off talking about the parts of the atom and different things about the atom. And so that's kind of where nuclear energy stems from. Let's look at isotopes. Okay, this is something that we talked about at the very beginning of the year. What exactly are isotopes? Let's kind of review that. Isotopes are different forms of an atom of the same chemical element. They have identical chemical properties, but their atomic masses are different. Also, their number of neutrons in the nucleus is going to be different. What is going to be the same for isotopes of an atom are their number of protons. That will not change, okay? But the atomic mass and the number of neutrons would be different. Some isotopes do occur naturally, and then some of them are made or created in a lab for research or for new products. Let's look at an example of an isotope, uranium-235. Now, when it's written in this form, remember the number that's behind the name represents the atomic mass or the mass number. If I were to take this number and subtract 92 from it, then I would get 143, which would be my number of neutrons, okay? This is a number that can change with different isotopes, okay? Now, what is radioactive decay? So, when these isotopes have too many or too few neutrons, then it can become unstable. And we've talked a lot about how in nature things like to attain stability. So when the nucleus becomes unstable, it will eventually break up. Then we say that the atom has become radioactive. So whenever you have an unstable atom, an unstable nucleus of the atom, where it either has too many neutrons or too few neutrons, that is when the atom will break up and it's going to become radioactive. They are releasing them to try to become stable. The energy in particles that are released during this breakup or decomposition is what we refer to as radiation. Radiation can be harmful to the body, but it also has many, many uses as well. Let's take a look at some of the uses of radiation. Here are a few uses that nuclear energy and radioactive material is used for. It's used for weapons. We've all heard of atomic bombs and hydrogen bombs. It's also used in fertilizers. It emits gamma rays for X-ray machines and readings. You have cobalt-60 and iodine-131 are used to treat cancer. You have food irradiation, which is where raw foods are exposed to high levels of gamma radiation and it kills the bacteria. So those are just a few uses of how we can use this nuclear energy. So although it can be very harmful to us, it also serves a lot of good uses. Okay, just another slide that kind of shows us some other ways that we can use radiation. Nuclear energy can be used to produce electricity. Okay, we have talked about that before. This was the one where it was referring to the food irradiation, where you can use that radiation to kill bacteria to make food safer. You also find a radioactive material in smoke detectors. It's actually used to activate the alarm. Okay, so just a few more uses of how we use radioactive material. There are three different types of radioactive decay. Okay, and decay is just meaning when that nucleus is kind of breaking down. There's three different types of radiation. The first type is what we would call alpha. Alpha particles is actually a positively charged helium isotope. Typically an alpha particle is going to have this form. It's just a helium isotope. It's a heavy particle, but it's very short range. It can travel a very short distance. It's actually you can usually stop this kind of radiation with a piece of paper, so it doesn't travel very far. Then you have a beta particle, which is actually an ejected electron. So when you eject an electron, that's just what a beta particle is. Beta particles can be stopped by about 6 millimeters of aluminum foil. Okay. And then you have gamma rays. Now, gamma rays are just pure energy. They're highly penetrating. They're actually electromagnetic radiation that travels in the form of a wave. And we call it a ray and not a particle. Several millimeters of lead are needed to stop gamma rays. They can be used to sterilize surgical equipment. They're used in the treatment of cancer. They are emitted in the process of fission and fusion, which we're going to get into that in some later slides. So these are just three different ways or three different types of radiation. So whenever you have those isotopes, their nucleuses become unstable and they start to break down. These are some different ways that that particle can decay. Okay, it can either decay and become an alpha particle, beta particle, or a gamma ray. Now this picture shows us the penetrating ability of some of this radiation. So in your space, in your notes, choose one of these diagrams to draw out to represent how these different radioactive particles can penetrate different materials. It doesn't matter which one you choose, but it just kind of shows you what these particles can go through. Like, for example, in this picture, we can see that our hand can actually, or our skin can stop an alpha particle. Beta particles can actually go through our hand, and then about aluminum is a substance that would be able to stop it. And then, of course, gamma rays, which we said is pure energy, is highly penetrating, so it can go through several substances. What is a nuclear reaction? Now, we've talked about different ways that isotopes can kind of break down, different types of radiation that are given off. So what exactly is a nuclear reaction? That's what we'll look at on this slide. First of all, a nuclear reaction is any process that changes the nucleus of an atom. So whenever you change the nucleus of an atom, that's what we call a nuclear reaction. And we talked about nuclear energy when we first started looking at forms of energy. And remember, nuclear energy is the energy that is stored in the nucleus of an atom. So whenever this nucleus goes through some type of change, we can say a nuclear reaction has occurred. A nuclear reaction can change atoms of one element into atoms of a different element. There are two main types of nuclear reactions. They are fission and fusion. Remember back on the slide with types of radioactive decay, we were looking at gamma rays, and it says that gamma rays can be given off during fission and fusion. Well, those are the types of nuclear reactions that we're going to discuss on the next slide. Now, this is a chart that has a lot of characteristics of fission and fusion. In your outline, you have a chart that is exactly like this. The only thing is that some of these categories here are not in the same order as they are on your paper. So just please make sure that when you are filling in this information that you are putting it in the correct spot in your notes. Let's talk about fusion first, okay? When you see the word fusion, or you think about something being fused together, what comes to mind? Well, if you're thinking about something coming together, then that is what fusion is. It's when two or more lighter atoms will fuse into a larger one, okay? The energy that's required in order for this to happen, though, is extremely high because you're trying to bring two or more protons close enough that their nuclear forces will overcome their repulsion forces, because we know that opposites attract, but like charges will repel each other. So it's going to take a lot of energy in order to get these protons that are in these nucleuses close enough to where they're not repelling each other in order to fuse them together. So it takes a lot of energy. But there's also a lot of energy that is released from these types of reaction. It's actually 3 to 4 times greater than the energy that you would get from a fission reaction, which we'll talk about next. Fusion can occur naturally. It occurs in the stars, such as the sun. Fusion is also responsible for the formation of all elements. The byproducts of fusion would be few radioactive particles would be produced from fusion reaction. So there are a lot of advantages of nuclear fusion reactions. Let's talk about fission. Fission is actually, instead of atoms coming together, fission is when you are splitting a large atom into two or more smaller ones. It takes little energy in order to split two atoms in a fission reaction. Unlike a fusion reaction, it takes extremely high energy. However, the energy released from a fission reaction is not going to be as much energy as you would get from a fusion reaction. However, the energy from a fission reaction is 1,000,000 times greater than that released in a typical chemical reaction. So you are getting a lot of energy from these reactions, but not as much as you would get from a fusion reaction. Um, Fission does not normally occur in nature. So fission reactions is something that would kind of have to be done by in a laboratory setting, for example. Okay. The byproducts, however, of a fission reaction are many highly radioactive particles, and they can be very harmful. So that is a huge disadvantage of a fission reaction over a fusion reaction. A fusion reaction does take a whole lot more energy in order to for this reaction to occur. Um, Both of these types of reactions are used in the development of nuclear weapons. In a fusion reaction, one class of nuclear weapon would be the hydrogen bomb, which actually uses a fission reaction to trigger a fusion reaction. And then in the fission reactions, the nuclear weapon that's able to be created are atomic bombs, or also known as the atom bomb. So you can see some advantages and some disadvantages for both of these types of reactions. Let's look a little bit more at nuclear fission. This is just a little bit more information about it and how it can be used. It's a reaction in which an atom of a nucleus of a radioactive element will split from an external source and release large amounts of energy that can be used for electric power generation. Okay, so we can use nuclear fission reactions in order to generate electrical power, which is where we would get our nuclear power plants from. Um, and they produce, in nuclear power plants, they produce heat through a controlled nuclear fission chain reaction, okay, which is just where you have a chain reaction. Is just where you have nuclear fission reactions kind of happening over and over again. So we can use fission in order to produce electricity, which is what happens in a nuclear power plant. A little bit more about fusion. Fusion would also be a superior method for generating power. However, well, let's look at the good and bad. The good is that the products, remember we said, of this type of reaction are not radioactive. There's very few radioactive materials that are given off from a fusion reaction. So that would be the good news about using this to generate power. However, the bad news is that in order to achieve fusion, the material would have to be in the plasma state. And we learned that the plasma state of matter is where a substance is at an extremely high temperature. And in this case, several million kelvins, okay, which would be an extremely high temperature. So that is kind of the bad news about using fusion to generate power. Let's kind of wrap up here with fission and fusion. Here are some diagrams that you can add in your notes. There is a box for you to put a diagram. These are kind of the simplest ones that I found within the slideshow that you could easily draw out. This one, of course, is the fission. This is where you have a large nucleus that will split into several small nucleuses. And then fusion, of course, is when you have small nucleuses that fuse or come together to make one nucleus. Okay. All right, so kind of switching gears a little bit now. We've talked about nuclear reactions and we've looked at fission versus fusion. Let's look at carbon dating, okay, which is also has a lot to do with radioactive decay. Carbon dating is actually a way of finding out the age of artifacts that contain materials that were once alive. So this is a really good way, depending on how a substance has decayed and how much carbon is actually left in that substance, scientists can actually tell how old an artifact is. As long as an organism is alive and eating, it will maintain a balanced ratio of carbon-14, which is an isotope, to regular carbon items. But once the organism dies, the amount of carbon-14 in the body is going to start to decrease. Now, after about 5,000 years is the half-life of a carbon-14 isotope. And we'll talk about half-life in the next couple of slides. But it's when about half of that original carbon-14 has decayed. So using this fact, scientists can actually tell how long ago an organism died by comparing, well, how much carbon-14 is left in this particular artifact or this particular material. Okay, let's kind of look at, we'll come back to half-life. Let's kind of look at this progression of pictures so you can kind of see how carbon dating actually works. Okay, so right here, this substance would have been a whole skeleton about 22,920 years ago. Okay. And then the half-life of it is 5,000 years. So after 5,000 years, about half of it will decay. Okay. So you can kind of see the progression here. So about 17,190 years ago, this is about how much carbon-14 you had left in the skeleton. And as you keep going, you can kind of see the breakdown of this carbon-14 atom. So this is a very excellent way of scientists kind of figuring out, well, how old a substance really is by looking at the amount of carbon-14 that's left in a material. Okay, so let's go back to our slides about half-life. Let's kind of go back just a little bit. Okay, so we said the half-life of carbon-14 is about 5,000 years. So what exactly is that? Well, half-life is exactly what it says. It is the time that it takes for one half of a sample to decompose or to break down. During one half life, or half of the radioactive atoms in a sample will decay. And this is how scientists, like we said, can determine how old materials are. Okay. There are several ways that you can look at half-life. You can look at it on a graph. You can also calculate it. And we're going to talk about both of those methods in the next couple of slides. So let's first look at how you can look at half-life on a graph. So let's get back to our half-life graph, which would be here. So determining half-life on a graph. All right, so this particular graph, it shows us the decay of 20 milligrams of O15. And our first question is, what will remain after 2 half-lives? Well, let's look at what the graph shows us. According to the graph, a half-life is about 2 minutes, okay? Because you can see here on the bottom, it shows us these arrows. And this is our time along the bottom axis. So our first half-life happened after about 2 minutes. So that means after 2 minutes, half of this radioactive material has decayed. So let's look here, because this is a way that we can kind of look at determining half-life from a graph, okay? Your initial amount was 20 milligrams, okay? So after 2 minutes, you're going to have half of that left, and we can see that here. You've got 10 milligrams left after 2 minutes. Then after 4 minutes, you've got half of that 10, which would be 5 milligrams, okay? And then after 4 minutes, you've got 5 milligrams left, okay? And then after 6 minutes, which is 3 half-lives, you have 2.5 milligrams left, okay? So you can kind of see the progression here on this graph, and it's showing you how after every 2 minutes, you've got half of your amount, okay, left, until eventually all of it has decayed. Well, how much would you have left after 5 half-lives? Because we stopped after 3. So how much would you end up having after 5 half-lives? Well, if we go back to the previous slide, after 3 half-lives, we had 2.5 milligrams left. So if I take that number and divide it in half, what would I get? Okay, if you said 1.25 milligrams, then you would be correct. All right, so that would be after 4 half-lives. So then I would take the 1.25 and divide that by 2, and I would end up with 0.625 milligrams. So you would just keep dividing that amount in half until you reached your answer. So on this one, the answer would be 0.625 milligrams would be left after 5 half-lives. All right, let's look at another one, okay? What percentage of the unknown material above is left after 3 half-lives, okay? If you said about 12.5%, then you were correct. If you go right here to this line, this is 3 half-lives, okay? And you kind of trace it over here. It falls a little bit below the 13. It's kind of hard to tell on this graph, but it's about 12.5%. So now, predict the percentage that would be left after 5 half-lives, okay? What would be left after 5 half-lives? Well, after 3 half-lives, we already know that there's 12.5% left. So if you take 12.5 and divide that in half, you would get 6.25. So 6.25% is what I would have left after 4 half-lives, okay? So then, if I wanted to know how much is left after 5 half-lives, then I would take that 6.25%, divide that in half, which would give me 3.125%. So after 5 half-lives, I would have 3.125% remaining, okay? So it's kind of like a pattern. You're just kind of dividing the number in half. Once you know how long it takes for a sample to decay, once you know what the half-life is, then you can just kind of take that number and you just keep dividing it in half. All right, calculating the half-life. And it's very similar to kind of what we were looking at on the graph. You're using that same idea. So for each duration, 1/2 of the substance decomposes. We've already established that. For example, let's look at radium-234. It has a half-life of 3.6 days. So after 3.6 days, about half of that radium-234 would have decayed. So if you start with 50 grams of radium-234, after 3.65 days, you would have, 3.6 days, you would have 25 grams left because that's half of it. And then if you go another 3.6 days, which would now be 7.2 days, you would have 12.5 grams left. Okay? So what if I keep going? After 10.8 days, how much am I going to have? All I would have to do is take this 12.5 grams and divide it in half, which would give me, if you said 6.25 grams, then you are correct. So the half-life for any substance is always going to be unique and constant. Well, we could also keep going here. If you say after 14.4 days, you're going to have 3.125 grams left. So you would just kind of keep going here. That's why it's always going to be unique and it's always constant. It's really a pattern, okay? It's really a pattern trying to calculate and figure out the half-life. All right, here's another one for us to try. It says the half-life of I-123 is 13 hours. How much of a 64 milligram sample of I-123 would be left after 39 hours? So if you get a question like this, this would be probably the best way to set it up, okay? You would start with the amount that you have at the beginning, and then after 13 hours, half of this is going to decay. So what's half of 64 grams? If you said 32 milligrams, then you were correct. I'm sorry, I meant to say milligrams. So what's half of 64 milligrams would be 32 milligrams. All right, so if I add another 13 hours to that, now I'm at 26 hours. So how much has decayed after 26 hours? Half of that 32, which would be 16 milligrams. Well, how much has decayed after 39 hours? Will now be 8 milligrams, okay? So whenever you're getting questions like this is the best way to set it up. And then you can kind of see progressively how much you have left after each time period. This concludes our video lesson on nuclear energy. Excuse for some of the interruptions and pauses that are in the video. If you need to go back and rewatch something, please do that. Make sure that you have filled in all of your notes on your outline.